This is John Black, super chemist. We're going to talk about the two types of inertial frames. Uh, an inertial frame that's in flat space-time and a inertial frame that's in curved space-time. And you might say, oh, I thought all inertial frames were the same. What are you talking about? There can't be two different types of inertial frames. There isn't. There's only one type of inertial frame. It's a frame where everyone's going at a constant velocity in a straight line. You know what I mean? But the space-time itself can be flat or curved, right? Like this box is in flat space-time. This is in curved space-time. What does that mean, curved space-time? It's got to be above a planet, right? And when you are above a planet, right, things fall radially in, right? So they're all going to be kind of, askew from being parallel to each other, right? The paths are going to look more like this, right? But, and over time, right, the balls will be together, right? When you travel through time, those two balls are going to move and they're going to go like that. These two balls are going to be the same length, distance apart. You might say, well, that makes this non-inertial. That makes this an accelerated frame of reference. No, it does not, because the balls are not accelerating towards each other due to being accelerated. Okay, we did the last video called two types of acceleration. This is the type that's about paths, right? In both inertial frames, everything travels in a straight line at a constant velocity. It's just that in this one, space-time's curved a little bit. So they're going to move in, geodesic straight lines, which are curved, or, you know what I mean? They're radially in. The balls are not accelerated, though, okay? Their paths are accelerated towards one another. Therefore, the ball stays inertial, right? When you just have you have two types of acceleration, one where their paths are accelerated and one where the objects are actually accelerated. If they're actually accelerated by force, then yeah, they're an accelerated frame of reference. But if it's just a happenstance, a coincidence, you know what I mean, the two paths accelerate towards one another, it doesn't mean that the balls or objects are accelerated or in an accelerated frame of reference. They're still in an inertial frame of reference. Right? Just like over here. Let's say this ball, right? I'm saying that this ball is moving at a constant velocity, 50 miles. This blue line and ball doesn't exist. Just this red line does. And he's in the middle of a void. There's no planets, no nothing anywhere near close by. He's a ball, so he don't have any rockets, right? He's going at 50 miles an hour on this path, right? We would all say that he is a inertial frame. He is not accelerated in any way, shape, or form. His path is not changing. His speed is not changing. Therefore, he is inertial, right? Just like in this example over here. The velocity the speed isn't changing. The direction isn't changing. It's a straight line. Therefore, it is inertial, right? Just because you have another ball here that so happens, you know what I mean? So now I put this ball here, and it's going 50 miles an hour. They're both going 50 miles an hour, right? Any two paths that's less than 90 degrees that cross each other, the paths are accelerated towards one another. And you can see right here with this example right here. These angles are equal, right? The angle here and angle here. And I drew a line, and I put up 3 hours, right? First hour, the red ball only accelerated this much. Look at this. Third hour, each hour it's moving more. It's not being uniformly in the direction towards to the blue line, right? So yeah, the path is definitely accelerating towards each other, which means the balls are accelerating towards each other, but they're not doing it because the balls are accelerated. They're just doing it because it's a coincidence. It's a happenstance. It's a whatever. You know what I mean? It's not because they're being accelerated in any way, shape, or form, right? This red ball we said was going 50 miles an hour. If I snap my fingers and now this blue ball exists and this path exists, it doesn't change if they're a million miles apart and this intersection is a million miles away. they're obviously not going to change anything. The red ball is still going to keep its same original path, not changing direction. It's going to keep its same constant speed. So he doesn't change its velocity in any way, shape, or form. He's still inertial. He's still going to be, if this was a spaceship and the ball was in a spaceship, the ball is going to still be floating. Whether this blue guy here is here or not, whether these paths are accelerating towards each other or not, they will still be floating in this thingy. And it's the same way with over here. It's the same exact thing. You just have two paths that are accelerating towards each other. But the balls themselves are not accelerating. They're just traveling in straight lines, and just so happens that they intersect. Whoop-de-doo, so what? That doesn't magically change anything. Just because this ball is here going, it doesn't magically change that ball's speed. Doesn't change the direction, because you can see it's still a straight line. And you can see down here, it's the same way with on Earth. If the ball, and this is Earth, right? The ball just travels a straight line. The Earth travels a straight line. The two lines intersect, just like up here. The Earth is still going, if you say, because if I snap my fingers and put the ball above the Earth, it's not orbiting, right? It's just standing still, right? And let's say it has the same momentum as Earth, right? It's going in the same direction, same speed, same whatever. We can say that they're standing still relative to each other, right? So these lines are just time, going through time. They're just standing still, right? And as they go through time, their paths cross each other. But they're obviously, if they're going through space at the same speed, so that we can call them standing still relative to each other, then they're going at the same speed. So they're going through time at the same, right? Their clocks are ticking at the same rate, right? So they're going at constant velocity through these straight lines, right? If they're going at the constant speed and they're going in a straight line, then they're not accelerating in any way, shape, or form, because you have to change your direction or your speed, and it's not, and neither is the Earth. The ball and the Earth are going through time. It's the same exact freaking speed. They ain't changing nothing. And since they're traveling on straight lines, then it's traveling on straight lines. Even though this one's curved, it's still a straight line. Okay? So, is there two types of inertial frames? Yes. Here's an inertial frame in a flat space-time, and here's an inertial frame in curved space-time. There are two types. But do they have different physics laws? No. Everything goes still, moves, everything floats still, everything moves in a straight line, right? Everything goes to the constant speed. The only difference is in curved space-time, the space-time itself is curved a little bit, so you're going to have, you're going to have this where it looks like they're accelerating towards each other, and they are accelerating towards each other, but neither ball is actually accelerating, right? Just the path is accelerating. They're following that path, just like over here. They're just following the geodesic. They're just following the path. They aren't accelerated in any way, shape, or form. Same one here. You can't say that you understand this story here, where the ball does not accelerate. We know the ball isn't accelerated just because this guy a million miles away starts going, and his path is eventually a million miles away is going to intersect. We know that it isn't going to affect this ball at all. It's not going to change it into being accelerated. It's still going to go 50 miles an hour, and it's still going to be on this path. It's not going to change. If you understand that, how can you not understand me when I talk about this? How can you not understand me when I talk about this? They're the same. They're all the same exact thing. Literally, I'm not even saying they're like kind of like they're similar. No, they're exactly the same. You have two lines, two paths that intersect one another in an accelerated way. But the balls themselves, that doesn't mean that they're accelerated, does it? No, it doesn't. If they keep their constant velocity and they keep by keeping their same speed and their same path, then obviously they're still inertial. What is so hard about it? Understanding this? I don't understand. Anyways, you all have a great day.